Hello everyone, welcome to the next lab of EC 573 Advanced Embedded Logic Design. In the previous lectures, we discussed about the high-level synthesis and how high-level synthesis can be used to create a hardware IP for the implementation on FPGA. So our focus is that for a given algorithm, how to create any stream interface or stream compatible hardware IP so that we can integrate with the processor or DMA for the acceleration on the FPGA. So in this lab, we are going to discuss about the HLS design flow and how we can export the IP, create the IP, then export the IP in the vivado IP catalog, and then build the block diagram and analyze or verify the performance on the zedboard. So with this, now we will start with the high level synthesis. Okay, so the first step is to open the vivado HLS. And once you open the vivado HLS, you will get the screen which is similar to the vivado. So then you should click on the create new project. Again, make sure that in the address here, there should not be any space. So I use the same the AELD folder which I have been using for the entire semester. Okay, so this is the lab 7. So we are going to create a AXI stream IP for the find function, which we discussed in our lecture session. So I'm giving the name as this. You can come up with your own name. Click on next. Here I'm not giving the any top function as of now. We can do it later. Again, test bench. I'm not giving any details as of now. You can add the files later. Now here you can see that we need to first select the board. So like we do in the vivado, we will go to the zedboard, and in our case we will select the zedboard from the digital. So then uncertainty. So here we can mention it as a 12.5% as we discussed during the during the previous lecture. And this is the name of the solution. So as I mentioned, for a given C code, you can create a multiple Verilog code by using the different constraint and directive. So for every Verilog code, you can give the different name. So here we are giving the first solution as a solution. Then click on finish. So you will get the screens, which is something like this. So you can see that there is nothing as such in this project. In the source one, you will add the your source C code, which you want to implement on the FPGA or which you want to map it to the hardware IP. In the test bench, you will provide the C test bench, and in the solution, you will get your Verilog VHDL or the hardware IP file. Then here you can see that there is a run C simulation. Then here you can see that there is a run C synthesis. So run C simulation means you will validate the functionality of the C code. Run C simulation means you will convert your C code to the Verilog code. And then you will see that the run C RTL core simulation. That means you will validate the functionality of the Verilog code. And then you will have the export RTL. That means you will convert your Verilog code into the hardware IP so that it can be included in the vivado catalog. Okay, so these 4 things are very important. So the first thing we will start is that we'll start with the creating the new source file. Okay, so here I'll start with the creating the new source file. So in this one, in this project folder, I'll create a new source file. So let's see, I'll say that the my name will be find function and AXI stream interface, or we can just say that the find code or find AP. Okay. So this is the okay. Make sure that you add the CPP as an extension. Okay. Okay, so you can see that in the source file you have the CPP corresponding CPP file has been added. Now here in this file we are going to implement our function which we want to map it to the hardware. So as I told you during the lecture session, we are going to implement the simple find function. So this is my find function where the input was value. Okay. And then another input was inject of say some dimension, and another input output was the outback of some dimension. Okay. Now you can add this dimension as a you can add it this value either in the C code, or you can create a corresponding .h file. So .h file is the better way where you can include all your definitions. So what I'll do is that I'll add another .h file in one new file, which is the find IP.h. It is always a good idea to have the separate .h file for every your hardware function. So in this .h file, okay, so what I'm going to do is that I'm going to define dimension as say 32. So my array size is 32. So I'll save it, and then here I need to make sure that I include my corresponding .h file. So hash include find IP.h. So now I'll get the value of this dimension from the .h file. Okay. So with this, now we need to write the functionality of this one. So what we are going to do is that we are going to do the for loop for int I is equal to 0, I is less than dimension I plus plus. Okay. We are going to read the corresponding input value in vect of I. If it is equal to 12, then out vec of I is equal to 1, else out vec of I is equal to 0. Okay, so this is my simple function. So you can see that this is a simple function where my input is of the type is a vector and the corresponding value. I'm comparing each element in the input vector with the value, and there is a match. Output is 1, otherwise 0. For now, for simplicity, I have defined everything of the type char, but you can define it as an integer or any other variable type depending upon your requirement. For example, you can define this as a Boolean also, or you can define the unsigned int of say 1 bit, 2 bit, or any number of bits. So those things we'll discuss it in the next half of the lab. So with this function, our function has been completed. Now here we have defined everything we want to do in the find IP.h file. There is nothing else is needed. Now we need to add the test page. So in the test bench, we need to verify the functionality of your IP. So what I'll do is that find testbench.cpp. Okay, so so this is the file we need to add. Okay, there is some issue here, so I'll just verify this one. Okay, so let's add the new file, then the find IP testbench.cpp. Okay, so I think I clicked on the add file instead of the new file. So now in the test bench, okay, the first thing is, since we will be using the printf statement and where we are going to use the input output, so we have to use the corresponding hash include stdio.h. Then we need to include the find ip.h, so that we get the information about the dimension. Okay, then we need to define our function. Okay, either we can define it in the find ip.h, or we can define it in the corresponding test bench here. So the test bench knows which function we are going to verify. Okay, so this is the function we are going to verify. Then the next thing is that we will write our test bench. Okay, so this is the test bench. Now in this test bench, it is very important. When this test bench, it should have the return 1. When the test bench is successful, you should return the 0. Then only your Verilog file will be generated, or hardware IP will be generated. If you return non-zero value, then the HLS tool understand that there is some issue in your code, and it will give you the error, and it will not generate any hardware file. So that's why you should use this return statement carefully. So the first thing we need to do is that we need to define some input. So again, character in vec. Okay, so this is of the type dimension. Okay, so what we'll do is that we'll try to define it as a some input there. We will define it using the for loop, or we can define it as a fixed value. That we will do it later. And then I'll have the out vec. I'll have it from the software, okay, as well as I'll have it from the hardware, that is from the C code. So then I'll have the out vec hardware dimension. Okay, and then we'll compare the difference between the two. Okay, so these are the function. Then what we need to do is that here we have defined the function. So let's initialize the input. So for int I is equal to 0, I is less than dimension, I plus plus, we have the in vector I. So here we can take some any value, say I into I or something, or say I plus 2, something like that we can do it. Okay, so so here we have initialized the input. Now what we need to do is that we need to call our function. which is the find function. In the function, there are three value. We can say that let's pass it as a 4. Then we'll pass the in-vec and we'll receive the out-vec hardware value. Okay, so this is what we have received. Now, so this is the call to hardware function. Input initialization. Call to software function. So what we'll do is that we'll have the find software, and okay, we'll just copy this by changing the name. Find software in vec and software, and I'll just write the copy of this function here. So this is the find software function implementation, and I'll define the corresponding software function. And ideally, what should happen? Both should give the same output. Okay. So we have called the function, we have implemented this one. Now I'll write another for loop. So in this for loop, I'll compare the software and the hardware. Software, if it is not equal to hardware, so in that case, we will print that error. Error for index zynq, that is I, and we will return 1. So that tool knows that there is a issue in the code functionality. If there is no issue, we will say that the printf no error. Okay, so this is our test bench where we have we are testing the hardware and the software output. Now, when the code becomes more complex, or you have the some software implementation in MATLAB or Python, you can create the golden reference, and you can check the output of the hardware with the golden referencing. Also, you can add the corresponding input files as well as output files to store the hardware outputs and the golden reference, and compare the data outputs in the files. So those are the things you can do it in case the things becomes more and more complex. Now with this, everything is done. So we have completed the coding part. So we will validate the software. Now, before we do that, we need to tell the HLS tool which function you want to implement in the hardware. For example, this file may have the multiple functions for the different type of architecture. So you need to tell the tool which function you are interested. So here you can see that I'll go to the project setting. Okay. And in the project setting, where I have the synthesis option, where I'm mentioning that top function. That top function is the one which I am want to implement on the hardware. So I'll click on OK. In the top function, I'll mention the function name and the click on OK. Then the next thing is that run C simulation. Then you will get a pop-up and click on OK. And once the C simulation, in the C simulation, your code will be verified. Now we are getting some error, and now we will verify, we'll validate, or we'll check what is that error is. So we are getting the error that we have set up the uncertainty to 12.95 nanosecond, which is higher than the clock period itself. So that's a problem. So what you need to go to the solution setting, go to the synthesis setting, and here you should change it to 12.5%. It should be 1.25. Okay, click on OK, and then click on run simulation. Okay, so you can see that there is no error in the C code. So C functionality is correct. So now we can go to the C synthesis. So then I'll click on the C synthesis. So our C synthesis is complete. So let's quickly look at the results. So it took 5.173 seconds. Your files has been generated. VHDL Verilog files has been generated. Some interface course has been created. Okay, so yeah. Now go to the solution. You can see that the target frequency we gave the 10 nanosecond, and the uncertainty is 1.25 nanosecond. But in each clock, you need only 6.195 nanoseconds. So you will meet the setup and hold time requirement. And total duration is 65 clock frequencies. So you will take 65 clock frequency to complete the operation. We have 32 elements. So each element will take one for the reading from the memory, because we are using the block RAM. And then once you send the data in the first clock cycle, you will get the data in the next clock cycle. So you will take 2 clock cycle for every iteration of the for loop, and one initial for loop to enter inside the one initial clock cycle to enter inside the for loop. Okay, so here you can see the loop details. So you can see that there is a loop for loop here, which takes the 64 clock cycle, and each iteration takes the 2 clock cycle, and the trip count, the number of iterations, is the 32. So that's why it is the 64 clock cycle. We can do the pipelining and all, but that will do it in the next lab. Here you will see the utilization. There is no need of block RAM. There is no use of DSP48. There are 21 flip-flops are used, and 67 lookup tables are used. So all the operations is performed using the lookup table. So your comparison circuit is implemented using the lookup table. So then if you want to know more about how this utilization has been done, so how the flip-flops are being used, you can see that since it is a sequential circuit, you need a FSM, so that's why you need 3 flip-flop. Then for some registers, you need additional flip-flops. Then for the register implementation, you don't need any additional flip-flops. Then multiplexers are there. You can see that the different multiplexers are there. So we can look at more details in the analysis, how which part corresponds to the which part of the code. And then here you can see that there are some control signals are generated, like clock and resets. Reset is active low. Then you have the start signal. So by using the start signal, you can ask the IP to start the operation, or you can connect it by default to 1. AP done indicates that the IP has completed the operation. It will go high for 1 clock cycle. So this can be used for, you can read this value as a by making this control signal as a AXI light port. Ideal indicate that the IP is ideal, and ready means IP is ready to perform the next task. So these are the control signal. You can ask the tool to remove this control signal if you don't want, or you can convert this control signal into the AXI light port so that each one can be mapped to the particular register, and you can set or read the status of the control signal. This value, you can see that the 8-bit scalar input. Now, as I told you that in the lecture, that all the input and output which are vector are assumed to be stored in the block RAM. So you, for the input reading, you generate the address chip enable and you get the corresponding input value. It's 8-bit because you have the character input, and the address width is 5-bit because you have 32 element. Same for the output, you have address chip enable, write enable in the output vector. So this is how your IP has been created. If you want to go into the analysis one, we can quickly look at what are the things are being shown in the analysis tab. So in the analysis tab, you can see that in the first, it takes 1 clock cycle to enter inside the for loop. Then your loop immediately start. So in the loop, you can see that you are, if you click here, you can see that you are initializing the I value. Then you have the comparison of the I value, increment of the I value. Then loading of the input takes 1 clock cycle because it is in the block RAM. Then you do the comparison of the value with the in vector. Okay, that value you have read in the first clock cycle, and then the output writing will be done at the in the second clock cycle, and this loop will be executed 32 times. So that's why there is a total 64 clock cycle latency. Okay, so these are the details you can see. You can also see the resource viewer, like what are the resources are being used. So you can see that there is a adder is being used, there is a multiplexers, comparators, and the comparators are being used. Okay. Then this is the memory read and the write ports are being used, and input output. You can see that the value you are reading, you are reading the input and you are writing the output. Okay, so all these details you can see. Then in the performance profile, as of now we have not done any thing. So in the resource profile, you will know which part of the code is taking what are the resources that is being mentioned here. Okay, so as the code becomes more and more complex, you will understand the importance of this analysis tool. Now coming back to our synthesis profile. So now our code is working fine. Now we will do is what we'll do is that we have already created the corresponding Verilog code. Okay. So this is the Verilog code. You can see that the Verilog code is very neatly written. These are the standard industry standard way of writing the Verilog code. Whenever we'll study the Verilog writing in our next course, digital hardware design, you will understand this in more detail. But at the end, you can see that there are the combinational circuit always at start, and there are the sequential circuit always at the positive edge of the clock. So your code is converted into the data path and the control path, and it's if you can read this code whenever you get time to understand more about how the code works. So for us now, we want to run the CRTL core simulation. With the CRTL core simulation, what will happen? You will validate the functionality of your Verilog code. So click on OK. So this process may take some time depending upon the complexity of the Verilog code. But in our case, since it is a simple Verilog code, it should not take more than a couple of minutes. Okay, so you can see that our RTL core simulation has been completed. Here you can see that we are not getting any error and it is successfully completed. Okay, so this is what the simulation. Now, if you want to look at the corresponding waveform in the vivado, you can I think we have not created the corresponding waveforms, but there is an option to see the corresponding waveform. I'll show you in the next simulation. I'll show you how to look at that waveform. Now, next thing is that we want to export the RTL, that we can click on here and we can get the corresponding hardware IP. But what we want to look at is that in our case, we want to have the AXI stream interface. But if you look at here, our IP is not having the AXI stream interface. It is having the native ports. So by using the directives, we can tell the IP to generate the AXI stream port. And this is very important to understand. Now, to enable the AXI stream port, there is a additional .h file which is provided by the HLS, which will help us to read the stream input at every clock cycle. Okay. So before that, before going into the IP, what I'll explain you the how to use the directive. Now, I can tell the tool that I want to have the AXI stream interface for this one. So what I'll do, I'll go to the right hand side option, directives. So you can see that in the directive for in vector, I'll click on insert directive. Then I'll tell the interface that want to have the interface. Here I'll click on source file. So that directives will be implemented in the source file. Then I'll say that I want which type of interface. So I'll say that I want an AXIS interface. Okay, and which is this port, in vector port. That's it. So now if I click OK, so you can see that I got the hash pragma HLS interface of the type AXIS. It is a register and it is having for the in vector. Okay. Similarly, I can do for the out vector, insert directive, click on interface, then source file, AXIS. You can see you can create a lot of other interface. We'll focus on AXIS and the out one and click OK. So I have got it for the output. Same thing, I can also have the stream interface for the value. I can have the stream interface or I can keep it as it is. But for now, we can have the stream interface for that also. Okay. So this is the stream interface. And click on OK. So that's it. Now I'm telling the IP HLS that I want to have the AXI stream interface. And what I'll do is that I'll do the run C synthesis again. Okay. Now let's see what happens. So make sure you have saved the file. Okay, so my C synthesis is completed. And you can see that now for every interface, it has created the data, valid, and the ready signal. So data, valid, ready, data, valid, ready. So that is what the basic AXI stream interface it has created. But from here, you can see that also my clock frequency has been reduced because stream interface is now you are replaced the memory interface with the stream interface. So it is much faster. So that is another advantage. Now the problem is that here there are two issues. One issue is that I don't want this control signal. Okay, I want to remove this control signal. And the second thing is that I want a last signal also for the in vect and the out vect because these are the array elements. So first thing is let's sort out the problem of the how to get rid of the corresponding AXI control, how to remove the corresponding AXI control port. Okay, so that is what we need to do. So let's go to the find here directive, click on insert directive, go to the interface, and here what I'm saying, AP control none. What does this means? I don't want the control port. Okay, AP control none, make sure it is in the source file. Okay, and click on OK. So another directive is implemented in telling the tool that I don't want the control interface. Okay, I'll save the file. Then I'll again run the C synthesis. Okay, and after the C synthesis, you will see that your control interface has been removed. Okay, now if you go to the interface, you can see that now all those control interface other than the reset and the clock are removed, and now we have this interface. Now for the value signal, which is only one scalar value, I don't need a last signal. But for this stream interface, I need a last signal, because to communicate with the DMA, last signal is very important. Now to add the last signal, we need to use the particular object which has been provided by the HLS. Okay, so for this we need to add some corresponding .h file. Okay, so go to the IP.h file and there include the corresponding HLS stream .h. In our case, we need only last signal, but in addition, in the stream interface, there are additional signals are there, like strobe signal, keep signal, ID signal. So those are all can be added, but for today's lab, we will just focus on the corresponding the last signal. Okay, in the future lab, if needed, we can add other signal. So let's keep it signal simple. We'll focus on the HLS stream signal. Now with this HLS stream signal, what it tells us that if you go into the HLS stream.h, it gives us the functions which will help us to read the values on the stream interface at every clock cycle. So by using there is a read and the write function, you can read the value in every clock cycle. So you can, whenever you see that the read, you will get the next value in the stream interface. Then when you say another read, you will get the next value in the stream interface. Similarly, you can do the write operation. So that's why this HLS stream is very useful. Now the next thing is that once you are the stream interface, now what you need to do is that the one where you need a corresponding stream interface with the last signal, you need to tell them that this is not a regular stream interface. This is the HLS stream interface. So you need to use this object HLS : stream. Okay. Then you need to tell the what is the data type and then the address of the first element, that is the in vector. Now here for my data which I am going to read, will have the valid and the ready has been separately defined. But now I need to define the corresponding data as well as the last signal. So what I'm going to do is that in my .h file, I'm going to define a structure. Okay. So this structure, so I say that the AXI is data. Okay. And in this structure, I'll have the two data types. One is the corresponding 32-bit of data and one bit of the last signal. Okay. Now this 32-bit of data, in our case, we want it to be the unsigned integer. For example, assume that one. I'll discuss this in our next lecture or next lab theory part of the HLS. But if I want to define it as a unsigned integer, what I need to use that I need to use the inbuilt data type, that is the uint, AP uint, okay, of the size 32, which is the data, And why this is important? Because in the conventional C code, you have only the AP int values of power of 2, that is 4-bit, 8-bit, 16-bit, 32-bit, because your processor works only on the power of 2. But in the FPGA, you can have the integer of 1-bit, 2-bit, 3-bit. So that's why this APU int is specifically defined for in the HLS for the FPGA implementation. And this is my last signal. Okay. Now we need to add the corresponding .h file to include this the corresponding data type, which is the AP in .h. Okay. With this, we will be able to define the corresponding data type. Okay. So with this, we have defined this one. Now what we'll do is that we will tell the HLS one that my data type is of the AXIS data for this HLS stream. And the same thing we'll do it for the output. Okay. So now what we are telling the tool that you need to create the HLS interface with the of the type AXI data, and then so that means your data part. So if you go to the existing here, now this data part will have the two subpart. One is your data, and the second is your what you say, last signal. So we need to separate out those. Okay. So what we need to do, we need to now read the this will not work because we are not receiving the vector, we are receiving the stream interface. Okay. So we need to make use of the read and the write function. So what I'm going to do is that for this AXIS data, I'm creating the local variable. Okay. So I'll say local read and local write, so that I can read the data of the stream interface. I can read the data of the stream interface from the stream input and store it locally. Then this local read will take the one sample at a time from the stream interface. So there is a function called read. Okay, so now I have read the value one at a time. So I have read the first value in vec dot read. Then I'll compare that in that local read value with the value. And what I'll do is that I have now local write is equal to 1 and the local write is equal to 1. But there is a mistake. Now local read is a structure, so it has the data as well as last signal. So I'm going to write into the data part of, I'm going to read into the data part, and I'm going to write the output in the data part. Okay, so this is the one thing. Now I want to also generate the corresponding last signal for the output. So when the last signal should be generated, it should be generated when the you are processing the last value. So if I is equal to dimension -1, in that case, what I'll do is that local write last is equal to 1, else write last is equal to 0. So this is how I've generated the last signal. Okay, data and last. So with this, what we are doing it here, at every clock cycle, we are reading the value from the stream interface. We are comparing the value and generating the output on the stream interface, and we are generating the appropriate last. Okay. So with this, now we need to verify the functionality. Okay, so now will there be any change in the hardware function? Now you can see that here it is not same as the previous one, right? Now you need to, in the test bench also, you need to generate the corresponding stream interface, because you can't pass the vector as a input to our hardware function, because hardware function is expecting a stream interface. So what we need to do is that, similar to the software, the hardware function, we need to create a local one. Okay, so what we need to do here is that this is the output of the software and the hardware. Then we will create a local read and the write. Okay, and we also need to create the corresponding HLS AXI stream for the in vector, because this is the interface type of your hardware IP. So this is the input stream, that is in vector, which we are going to pass to the hardware. And similarly, we need to have the out vector. Now our code definitions will also change for the hardware function. So we need to change this to this. Okay. So our software function will remain the same. The hardware function will change. Okay. So this is not at. This is, we are giving the address, so it should be add here. Okay, so this is the one. So basically now in the call to the function, it should be the invec here, and this is the outvec hardware. Okay, so I'll remove this part here. We don't need to define this anymore. Okay, so we have defined the input array. Okay, now we need to convert this input array. Okay, invec is there. Here input is there. So I think that we need to use some different names here to avoid the. So for time being, what we can do is that here we can write input and output the ambiguity. So here we need to have the input and output. Okay. So this software part is same here, but for the hardware part, we need to pass the corresponding. We need to pass the corresponding input in terms of the stream interface. So basically, we need to convert this in the stream interface. So what we are going to do, for integer I is equal to 0, I is less than dimension, I plus plus. Okay, so this is what I'm going to do. I'm going to read this one and create a corresponding stream interface. So local read of data part of the local read is equal to the I'll get the in vector I. Okay, so this is my local part of the data input. I'm going to assign the value there. Then I need to generate the corresponding last signal. If the dimension value is equal to 9, I'll make the local read dot last is equal to 1, and else local read dot last is equal to 0. And then what I'm going to do, I'm going to pass this to your stream. So this is my input vector stream. I'm going to write to that stream, okay, which I'm going to pass to my hardware function, and I'm going to write the local read signal. So you can see that I'm going to create a stream input with the data and the last signal of the 32 values. So this input, I'll going to pass it to the hardware function. So whenever hardware function reads the input, this guy is going to provide the input to that hardware function. Now, after I complete this, I'll get the stream output from the hardware. So now while comparing, I need to, because this is a stream output, I can't compare it directly. So what I need to do is that I need to have the output local, use the local read function. Okay, so I'm going to use the local write. Okay, so local write, what I should do is that output vector, this is the stream one. I'm going to do the read operation. So there is a read operation is there, which is the output vector hardware dot read operation, and I am going to do into the local write. Okay, so in the local write, I'll get the one, and then I'll compare it with the software. I'm going to do the local write, only the data part of the software. Okay, so with this, we are done with this one. So basically, whatever we did in the stream interface changes in the code, you need to appropriately generate the input in that format for the our hardware IP in your test bench. So with this, we are done with the code. So now let's do the run simulation. Save the changes. Okay, click on OK. Okay, so we have got few errors. I think they are mostly because of the data format. So we have not taken care of the data format while assigning the value. So make sure that when you do the assignment, you do the appropriate data format mapping. So for example, here I need to make sure that I typecast the data to the APU in 32 here. So this should be APU in 1 bit and APU in 1 bit. So we need to make sure we make these changes. Okay, another major error we did here is that while reading the data, we read the entire structure. So we should read the data part of that structure. So that is another error we did here. So that we should correct this one. Let's verify there is such error here. We are reading the data part here, writing the data part, and that is fine. We are reading the local write and data. Okay, there should not be any issue now. Okay, so there are few mistakes we did during the writing the code. So first thing is that when you are reading, you should read the entire structure. Here we were reading only the data file. That is not correct. So read the entire structure, and while comparing, compare with the data value. Also, we didn't, once we have the output data generated, we didn't write it to the stream interface, so that we need to use the write function similar to the read function while reading from the stream interface. There is a write function. Okay, so just let's comment this code. First pragma is to remove the control interface. You can convert this control interface to the AXI light as well, but we will discuss it sometime later. This is to create AXI stream, only the valid, ready, and data for the ports. Now, local data structure for data and last signal. Okay, this is the local. Then read one sample of data and last over input stream interface. Okay, compare the data with val input and generate output data generate last signal for output stream. Generate output for stream. Okay, generate one AXI transaction for stream output using data and last signal. So basically here on every clock cycle, we are putting the data on the data bus, last signal, ready valid signal, and best when the ready signal comes, you have the handshake, and this will happen 32 times. Okay. So with this, let's do the run C simulation. Okay, C simulation is completed. Then what I'll do is that I'll directly do the RTL core simulation that will do the C synthesis along with the CRTL core simulation. Okay, so the RTL C simulation is completed. I can show you the synthesis ports, and now in the synthesis port you can see that the corresponding last signal is generated for the input and the output. This is very important signal for the AXI DMA interface. Now, after I completed this one, now I'm going to do the export RTL. Okay, in the export RTL, I'll have the IP catalog in the Verilog as a HDL language, and I'll click on OK. So now this export RTL gives the error. This is because of the problem in the vivado tool that has happened because of the year change from 2021 to 2022. So to avoid this one, what we need to do is that we need to do certain changes in the setting. Okay, so in the IP catalog, go to the configuration, and here if you try to see that if you can change the version to 1.1.0, let's see if it works out. Otherwise we'll try to find some other solution. Okay, that has been successful. So our RTL has been generated and the corresponding hardware IP has been generated. So you can see the details about the hardware IPs are available. Now this HLS part is done. Now we will close the HLS and we will move to the vivado.